We saw in the previous exercise that using a PDE toolbox we are able to solve very simple Laplace equation which is a model for a capacitor problem, and we also saw the impact of the discretization, how it is impacting on the resolution, whether it makes sense to go finer for a simple problem, so on and so forth. And I mentioned now we will look into a problem where refining the grid makes sense, and we have chosen the problem specifically for that particular reason, so that we are exaggerating the impact of discretization in the problem resolution. We are going to again start with the Laplace equation. Now instead of having a parallel plate like in the case before, we are going to use a different kind of capacitor. It's not a parallel plate capacitor, whereas it is going to have a kind of a dip, a conical dip, and the reason for doing that is in the sharp edge here what we see, the resolution of electric potential and also the potential difference is going to be difficult because the sharp edge itself will create certain inaccuracy and some singularity in some case. So we are going to see how we can model this problem using the PDE toolbox, which is an inbuilt functionality of the MATLAB. So let's start looking at the problem itself in the MATLAB. So we are going to start with the MATLAB code that has been written to generate the mesh in the form of a PDE model. So now we are going to run the geometry generating or the PDE model generating PDE function, and we are going to get the mesh that we want. So initially we will start with a very coarse mesh. This is a geometry that I have described on paper, and we are now using this geometry and we are meshing it, and we have kept very coarse discretization as you can see, and we are now going to export the mesh as a PET matrix, and now we are going to close this one, and then we are going to go and save the home workspace in terms of a material matrix. So capacitor, conical problem, mesh data, cone, save, replace. Now we have saved it on a particular folder, and now what we are going to do is we are going to go and run the MATLAB code that we have written for the problem. It's a conical capacitor, and we are using FEM, the unstructured mesh, and it's going to do the same thing what we saw in the earlier module. It's going to start with the PET matrix, and it's going to assign the elements and edges and nodes accordingly. It's going to display the number of elements, display the number of edges, initialize the C matrix as a sparse matrix. This is done in order to make the program faster. This has been done to make the program run faster, and it is initializing the source vector, and it's going to go and compute the local coefficient matrix. It's computing the delta, which is the area of each of the elements, and it's substituting the value that has been computed for the local coefficient matrix, and once it comes out of the loop it goes into concatenation process where it is going to join all the local coefficient matrix to create the capital C, which is going to be the global coefficient matrix. Once it is done, it is going to apply the boundary conditions. We said that in our problem, let's go back to the sheet. So our problem is going to be this manner. We have set the top plate to be at phi is equal to 1, the bottom plate to be at phi equal to 0 volt. So these are the boundary conditions that we are setting, and this you can see also in the earlier part of the code where we have clearly said what is going to be our potentials. So this is going to be given as V1 and V2. So we are setting the top plate to be 1 and the bottom plate to be 0. So these are the boundary values that we are giving, and we are going to see the result solving for the magnetic vector potential and also plotting the electric potential in each node, and we are going to see how the electric field intensity is being displayed, and we are computing by calculating the gradient, and the value that we are getting is nothing but the plot for the electric field intensity, and we are plotting it as a function of PET, and the value E is computed according to this equation. So we are going to run this program now to see the outcome of the program. So what we can first see is the number of edges, nodes, and elements. So what we have is, for a coarse grid, what we have chosen, the number of nodes, which is written as n, is going to be 143, and the number of edges, E, is going to be 46, and the number of elements, which is a T, which is going to be 238. So I have written this down so that when we compare it for a next discretization, we will see what is the number of nodes, edges, and triangles what we have. So what we have gotten is two things. What we have got is solving the magnetic vector potential and plotting the electric potential at each of the nodes. What we see are two graphs. So let us look into the graphs or the plots what we have got. So the first one is the potential. What we see is the top plate, the conical plate on the top is having a 1 volt on the top, and then we see that the bottom plate has 0, and we see that the equipotential lines are no longer straight. Closer to the conical plate it is going through a curve, whereas at the bottom plate it comes to a straight line. And what is also interesting to see is the electric field itself. What you see here as electric field, it shows certain high value at the tip of the cone. So we said the top plate and the bottom plate at the point of the tip of the cone is going to be between 0.5 and 0. So the distance between the top plate, the conical point of this plate, and the bottom plate is roughly 0.5, and we said that the top plate is at a potential 1 and the bottom plate is at a potential 0. So the electric field at this point should be approximately 1 divided by the distance between the plate, which is 0.5, which should be 2, should be the actual value. So now with that in mind, let us see the actual scale of this thing. So let us put the scale in place. So when I run the program, so I am going to run the program for the coarse discretization what we have got, and what we see is two plots, and we also see certain parameters that are important for us to note. So what we get is the number of nodes is 143, the number of element is 238, and the number of edges is 46. That is what I have written here in the paper. So this has been done for the coarse grid, and we will do a fine grid example where we will see the number of nodes, edges, and triangles are going to change, but let us see the result itself and see what is the result telling us. So you see that the potentials on the top plate is at 1, the bottom plate is at 0, the equipotential line towards the conical plate is curved as we expect, while it changes to a horizontal line as it comes to the bottom plate, and we also see that the curving is gradually reducing, the equipotential lines curving is gradually reducing as it comes down, and it also changes, the curvature changes as we go away from the conical point towards the edges, either edges. This is an important point which replicates the physical measurable result. And let us look into the electric field itself. The point that one has to know here is the potential at this point here is 1 volt. The potential here is going to be 0 volt. The distance between these 2 points is 0.5. So we know the electric field magnitude should be given by the voltage divided by the distance roughly. So the voltage difference is 1 and the distance is 0.5. So we should have a value which is in the range of 2 volt. Let us look at the result itself. What you see is it is definitely more than 2 volt. It is in the range of 2.5 volt or maybe even more. So that is the inaccuracy that one sees when we have very sharp discontinuities. We should be in this range, in the color range, whereas we see that it is definitely above 2.5 volt. With that in mind, let us go now and do the same problem for a finer grid and see how the result is going to improve. So for that I have to go back to the PDE toolbox and I am going to run it again. So we are refining the grid. Remember, initially we had a grid of this coarse discretization. Now we are going to refine it, and now it is very refined, and we are going to mesh export. We say OK, we exit, no, and then we go to the home, we go to the workspace and we save the workspace, conical problem, mesh, data, cone, and we are going to save it, going to replace it, and we are going to go back to the finite element code and run it, conical FEM, and now we are going to run the program, and we will start noticing that it is going to take a long time than before, slightly longer, not that much longer, but slightly longer. What we can see is the number of edges, number of points have changed dramatically. So let us go back to the paper and see that in the first example what we had 143 number of points, nodes, edges were 46 and the triangles were 238. So let us look at this particular problem here. You see the number of nodes have been increased to 7801. The number of triangles are going to be 15,232, whereas the number of edges are going to be 368. So what we see is there is going to be a substantial increase in the number of elements, number of edges and number of nodes, and we also see that how this is going to affect the value of our result. If you see the potential graph itself, it does not change much. It is pretty much the same way we saw before. The equipotential lines are pretty much the same. We see that towards the lower plate it is changing to be horizontal, whereas when it goes towards the conical plate it sees a curve, and the potentials on the top plate and the bottom plate are exactly what we have given. The result is not categorically different. So in this case we do not win much, whereas if you see the way the electric field is plotted, what we also see is overall we get very good result, whereas what we see in the tip is the singularity is very sharply reflected. What you see is a value that is more than 5 in this case. In the coarse grid what we got is roughly 2.5, whereas in the fine grid we are getting a value that is more than 5, which is ridiculously wrong. So what we wanted to show here is, in some of the problems you gain something by refining, whereas in some of the problems the gain is not there, pretty not there. There is going to be a lot of other things happening. This is also something we saw in the case of finite difference method. By refining the grid, the error is going to increase because of various other reasons. For example, the number of points that we are going to use in the computer is going to increase dramatically, and because of that the truncation error or the numerical accuracy is going to change accordingly. So remember the curve that we had in the case, refining will lead to reduction in error because of one reason, whereas it's going to increase the error for a different reason. And that is what we have also showcased in this case. Although we have refined, globally the solution is in a good way, it's replicated in a good way. The electric field in this point and this point is nice, but whereas at sharp edges the error is exaggerated much beyond our expectation. You see that it's going to a very high value. So what will happen is, if you go even finer, the discretization will create a very high value which goes counterintuitive. So this is a problem that we wanted to showcase where we actually win in terms of reducing the discretization or increasing the discretization, making the grid more finer or making the grid more coarser. In some cases we win, in some cases we don't win, and this is something is counterintuitive. People don't really know this until they simulate it and they think the program is wrong or the code is running wrong. No, it is, everything is okay. The only thing is the nature of the numerical method is like that, and particularly in the FEM case this is very much like the case. So one has to get a physical sense of what will be enough discretization, what is good enough, and how we can model it depends on the experience that you gain by running such programs. So what I would encourage is, I would like you to look into this program, model it for yourself, practice it a bit and get a good sense of how the program can be used for your type of problems. So whether it could be a simple parallel plate problem, or it could be a conical plate problem, or any sharp discontinuities that you might encounter in real life applications. So with that being said, we have covered enough in the last few modules using finite element method, and we have showcased the various pros and cons of numerical method of finite element, and also we have seen the pros and cons of using finer grid or coarser grid. We will use the same problem and we will approach the same problem using a different method while we come and do the module of algebraic topology later on, but it's important for you to know this problem will be a test problem for you to see whether the refinement is making sense or not. With that being said, we'll stop here and we'll come back and do some more problems in finite element at the later modules. Thank you.